stuff out of the way. Right. So today's topic. This is the 36th webinar that we've run on a series of projects that we've mostly funded. And today's topic is current state of knowledge on the risk of induced seismicity at CO2 storage projects. And so we begin. We have three presenters today. And the first of whom is Seyyed. Hang on, I'm just do apologize for this. Yeah, here we go. The team at Bureau of Economic Geology at the University of Texas at Austin were contracted to do this report for us. And three of the researchers who worked on it are presenting today. Seyyed Hosseini, who's senior research scientist, did a lot of the work. Alexandros, Savvaidis, and I apologize if I mispronounced your name, is project manager and seismology research team lead at the IEAGHG, Bureau of Economic Geology, and Sue Hovorka, who's a senior research scientist. And if you've been to many of our network meetings and reports, Sue will be a familiar face to you. So today, Seyyed's going to introduce the report and explain its contents, and it will be publicly available, I suppose, in about 3 months' time. Alexandros is going to run through some basic definitions of seismicity, and this is important because there can be some misconceptions, and we all need to know the correct language when we're talking about seismicity. How seismicity relates to carbon capture, utilization, and storage. Sue is going to cover that topic. Then Alexandros will be covering seismicity related to water injection, the significance of which will be explained. We then go back to Seyyed, who will be talking about the regulatory framework, and then Seyyed will also talk about outreach. And then we will have time at the end for questions and discussion, and I would encourage you to submit your questions in the question function on your our webinar. Go to webinar function. So just point that we always present the disclaimer just to distinguish ourselves from the IEA in Paris. We are affiliated to it, of course, as all technology collaboration programs are, but we are legally functioning, legally autonomous. So these views and findings are not necessarily the views of the IEA Secretariat. And for those of you perhaps new or have not heard of us before, we are a technology collaboration program established in 1991. We were set up to provide information on the role of carbon capture and storage, and indeed other greenhouse gases. And like all TCPs, we adhere to the basic principles of objectivity, trustworthiness, independence. And although much of what we produce is policy relevant, we are not policy prescriptive. Policy, by and large, for this and other technology collaboration programs is the function of the IEA, and all our work is externally reviewed. And As you can see, we have a number of countries and companies. From the logos, you can see there are many well-known big names that support us. They have clear interests in what we do, and in fact, they decide what projects which are commissioned. And this webinar, along with all our other activities, is very much part of a knowledge transfer function that we have. We do engage with a number of other organizations. We are represented at COPS, for example. We input to ISO standards, London Convention, and last but not least, we organize the largest CCUS conference biannually. And if you weren't already aware, the GHGT 16 will be held this October in Lyon. And I would urge you all, now that bookings are open, to book your place there. And with that, I will hand over to the BEG team.
All right. Could you hear me? I'm just double checking.
Yes, yeah, we can hear you.
You can see the screen? Looks good?
Yes. Yeah.
All right. So thanks, James, for the introduction. As you mentioned, well, this is a report on the state of the knowledge regarding to the Induced Seismicity for the CO2 storage projects, and also some experiences on saltwater disposal. I also wanted to acknowledge two other collaborators that we had on this project, Florentia Kavura, which is, she and I believe at the University of Delft, and JP Nico is also a senior scientist in parts of the. All right. Let's see if I can run it. All right. I thought it's going to be a good idea just to put the content of the report as our first slide for everybody. So we will be covering parts of this report today based on the time that we have. But as James mentioned, the report is going to be publicly available, and for more information, you guys can basically get a copy of the report and go through more details. Our plan is today that Sue is going to cover basically the chapter 2 of this report, which is the current state of the new seismicity and CCS projects, and looking in the catalog that we prepared for this. Then Alexandros is going to cover a bigger part of this presentation, which will be looking at the more of a technical background of the induced seismicity from saltwater disposal, which we believe is very similar to what we will be seeing in as far as the large volume injection of fluid in the subsurface is going to be. And as you can see, there is a good technical content is going to be there. And then I will be just providing at the end a quick examples of the regulatory oversight on induced seismicity. And I believe I have like a Oklahoma case for you guys, and also an example of the outreach methodology and why they are important. And for that one, I will be reviewing the Tomokomai case. And we will have some couple of slides on the concluding remarks and at the end of the presentation. With that, we start with a few definitions, and I think this is for you, Alexandros, to just get us going with some basic definitions as far as the induced seismicity goes.
Thank you, Seyyed. Thank you, James, for the introduction. So just a couple of terminology parameters here to make sure that we things are clear to everybody. So first of all, these small events that are caused by pressure elevation is called microseismic. That's our very small events, usually magnitude of lower than 0.8, and those are not felt events. And then in some cases, of course, they are related to unconventional resources recovery. It is related to fracking, because the frac process is up to creating so small events in order to open the cracks and get the oil out of the cracks. it is important to avoid any confusion between low magnitude events and felt seismic events. So that's why the low magnitude events are usually referred to as microseismic events. Those events are usually above 0.8 or magnitude 1, but less than magnitude 3, because magnitude 3 is in some cases it has to be, relates to the limit of where the seismicity starts being felt. Of course, there are a very few cases where we have smaller magnitude events, lower than 3, that are being felt, but these are very rare and usually related to site amplification due to the soil amplification that we have at the site of observation. Now, induced seismicity events are earthquakes that caused or relate to human activity and that exceed the background seismicity level. So each area of interest at the time of interest has its own background seismicity level. And when we are due to human activity in the same area at the same time, we have an increase of the seismicity level, and this can be considered as induced seismicity. Microseisms are not considered induced seismicity earthquakes. Just to clarify this, as I said earlier, they are very small events. They are not felt, and they are part of some of the human activity, but they are not considered induced seismicity earthquakes. Next slide. Seyyed, are you okay? So the most common source of induced seismicity is the unconventional resources recovery. Just to point out here that although the small magnitude less than 0.8 magnitude events are not considered induced, in some cases, because of the stress changes in the area of the unconventional recovery, we have faults that are the vicinity of the lateral wells where they got activated, they slipped, and in that case we start having some higher magnitude events which can be considered induced seismicity. Produced water injection is a salt water disposal. It's also a source of induced seismicity. We will discuss more details later in this presentation. We know that also in the hard geothermal systems where we frack the rock, they also create, they might be creating high magnitude events. And also mining seismicity is pretty common for a long time now. And recently we have seen a very few cases with CCUS induced seismicity. Next slide. I think Seyyed, that's...
Yeah, I think at this point we switch to Sue to give us some review of the state of seismicity of the CO2 storage projects. Sue?
So thank you, Seyyed. I undertook this part about monitoring the what had happened at the storage sites in terms of seismicity, and I was initially quite pessimistic. I hadn't heard of very much information, and I thought we were going to have to heavily rely on the water injection analogs that in order to, because seismicity is not, induced seismicity is not very common. It's geographically restricted to areas that have a sufficient state of stress to create induced seismicity. I thought that the portfolio from CCS projects was going to be so slim that we couldn't say much. So I inventoried 49 projects that were for which there was some information available. A lot of it I called people to say, really, did you really do nothing about seismicity? And the answer was actually very cheering, that many projects had made measurements of some sort. So we had 36 of I talked to 49 projects, and of them 36 had made some sort of measurements related to seismicity, which is shown in the next slide. So this is any kind of detection at the site we're counting here, and I note the ones that this rather sparser population that has more detailed reporting is listed for further reading. I'll show you just a couple of examples of this. That the ones that have minimum information available are depleted oil and gas and EOR settings. It's not information on induced seismicity or seismicity at all is not collected, generally associated with EOR. The major outlier is the well-known Cogdal field, which has had quite high magnitude seismic events related to both water injection and then CO2 injection for enhanced oil recovery. Important thing for everybody to know is that Cogdal is still in operation. The monetary value of the recovery is sufficient to offset any stakeholder opposition. It's not a very populated area, so the seismicity is just tolerated. The injection operation continues in spite of inducing seismicity. The sites that have sparse information are many of them are very small. Didn't have a budget to bring out measure seismicity. So there's quite a lot of data, and it's rather reassuring. The reason you don't hear about it very much is because nothing much was found. They were able to make some measurements of some sort, mostly reporting that they couldn't separate out any microseismicity from ambient noise. That when we the next slide, I'll show you, talk a little bit about the most one of the good examples that, I mean, I shouldn't say good examples. One of the examples where the microseismic measurement was informative, useful, and produced data that could be analyzed extensively was the Illinois Basin Decatur project. This is in Decatur, Illinois. You're seeing the facility at the surface. During this first phase that's shown in the data collection, they were injecting 1/3 of a million tons a year for 3 years, so a total of 1 million tons a year into the Mount Simon Formation. They were able to identify some events that are shown on the surface, in the subsurface. They're relatively small magnitude, but detectable so that you can locate them well. And they're within 200 meters of crystalline basement below the injection zone in the Cambrian. There are related trends in the basement topography. There's been reluctance on part of the team to overinterpret them, but since I'm not part of the team, I could say that the basement is fractured. These probably show fracture orientations in the basement that are being that are under stress and are being energized to produce microseismic events as related to the injection. The microseismic events continue after the injection, as is conventional, show a relationship, but it's not one-to-one with injection, because when the second injection, which is to the north, no, back one slide. The reason I'm not showing it is because there's not much data. When they moved the injection point higher up the well, the microseismic events dropped off to negligible and became hard to locate again. Apparently the key thing in this project was the proximity to the Precambrian basement is what caused it to create microseismic events. Notice this is not a problem. This could continue indefinitely, but it does tell us some interesting things about pressure and how it interacts with the state of stress in the different rock units. It doesn't cause seismicity in the sedimentary zone. It causes seismicity in the more brittle basement. Okay, next slide is the project we ran. We thought this project, perhaps we could get some nice geomechanical events, and we invested deeply in monitoring. There was a great more than 1 million tons of CO2 injected per year into it. It's a depleted field, but it had recovered so that it was an initial pressure. So it's very analogous to a saline injection at the early stages before production became important. The operator took the pressure way high to 1,000 psi, more than initial pressure, and it has a structural central graben in the area shown. It's got a graben, 2 large faults at reservoir depth. So we thought we would see some interesting geomechanical effects, and we were we partnered with a number of people. The one I'm talking about here is an installation by the Wright in Japan, who monitored for 3 years. They placed their high-end seismometers at 100 meters depth, and the young researcher who was doing this was very disappointed not to be able to measure anything. The instruments were working correctly. We saw natural events. We saw check shots, but and she deduced the sensitivity was about 0. So we could see background noise, lightning. She'd call and say, "Is everybody okay? I see the lightning," because it's quite a area of summer storms, or this is Mississippi. So this one is kind of the high end of the typical population, where the measurements were made, but they were not particularly informative of anything happening in the subsurface. We know that there is some noise related to injection, because if we put on headphones, we can hear things we can hear it sounds like a faucet running where the CO2 is coming out of the injection well. But we can't locate them very well. We can't analyze them. They don't tell us much about the state of stress or opening of fractures or this kind of thing, because the events seem to be low magnitude and also not related to events. So that's the fairly detail of the typical population. There's more details in our report about all the rest of them. I think that's it for me.
All right, thanks, Sue. Yeah, I think the next part is looking at the experience from the saltwater disposal in Alexandros. You're up.
Thank you, Seyyed. So I'm going to describe the induced seismicity information we have from water injection. There are a lot to describe here and much more in the report. So please refer to the report if something is of interest, and of course we can discuss at the end if something is important for you to discuss today. Now, this is let's say a sort of summary of my presentation. In the beginning, I'm starting with the new practices developing in the United States. Seyyed, can you move forward? So an earthquake program should have 4 primary goals. Those goals, the first one is the monitoring analysis of earthquake activity. This is really very important, especially when we have no information about background seismicity in the area. The second thing is everything that is related to hazard and impact of seismicity. So we have to create local ground motion models. Maybe the general ground motion model used in hazard assessment there does not fit the specific area. And of course, it's good to identify if there are any soil amplification models related to the area of the observation. The third goal is the seismicity causal factors. Now, for that, usually we go with 2 approaches. One is the most common one, is the spatiotemporal seismicity clustering and well association. And the second one is the physical mechanisms of induced and triggered seismicity. For that, we can use actually physics-based simulation models to understand what we see and relate their seismicity to possible causal factors, or even can be used for height casting for future seismicity. The fourth part is how to enable the risk mitigation. This is also important. For that, you need to identify the active areas of seismicity, develop your own statistical and empirical models for hazard mitigation, and of course, report regularly the spatiotemporal seismicity distribution. Next slide, please. Now, specifically for the US, the last few years, what we see as important practices is to improve the assessment of earthquake source information, and that does not relate only to the epicenter location, but accurate hypocentral depth, because depth is a key parameter for causal assessment, and also identifying the fault rupture zones. That means that identify the size of the subsurface rupture area and the fault type, because fault type is important also for seismic hazard assessment. And the second important thing that we see in the US is that we have to create a data-rich database of injection-related information. And here in TextNet, we have an example where the operators provide daily injection volumes and pressure monitoring data that are available to the public. Other than that, also information related to the information types and the depths is important, and also information for the hydrological characteristics of the formation, for example, permeability is important, and the boundary conditions in order to define to create any simulated model. Next slide. Now, earthquake catalogs. I added this slide because I would like to clarify a few things about earthquake catalogs. You hear the word earthquake catalog a lot of times, but there are a lot of different types of catalogs. So I will go through this to describe them. So the first type of there are two main groups: the absolute location approaches and the relative location approaches. The big difference between those two is that the absolute has all the information, and they are the location algorithm is driven by the fact to identify the best possible location, accurate location on the of the earthquake source information. The relative location approaches, they use some let's say mathematical approaches in order to identify mostly the lineament that follow the fault strike, and also somehow the subsurface area, but they don't have the accuracy of the absolute location. Actually, what is happening is the relative location accuracy somehow depends on the absolute location approach, because the former, the absolute location data, is the input to the relative relocation approach. For the absolute location approach, we have three cases. The first is the automatic that we get about our earthquake management systems, that is coming out in a few minutes, the fast estimation that we use of earthquake source for our operations. Second approach is the manually reviewed earthquake source information that's coming out a few minutes or a day after the origin time of the earthquake. And the third one is the high precision earthquake catalog, where we come up after a few weeks, where we try to keep as much as possible the absolute location approaches, but try to get more high precision locations in order to identify the subsurface rupture area. And then any of those three can be an input to the relative relocation approaches, where we can identify the fault plane. Of course, as more high precision is your absolute location data, then more the relative relocation approach will be more successful. And next slide. And here is an example. On the left-hand side, you see the manually reviewed absolute location we have from our analyst. That is for a site in West Texas, where you can see there is a diffusion of seismicity in space. And on the right-hand side, you can see the data that we have used as input on the left-hand side, how we can create the relative relocation catalog, where you can see here that clearly we can identify the fault strike direction and the fault projection to the surface. Next slide. So why do we need all that? First of all, we need all that just to identify the active faults and their characteristics. Of course, that's important for us, because if we know where are the active faults and what are the characteristics, when we can see, we can use this information for any causal analysis, first of all, and then if we can use it for risk mitigation. Also, we need to ensure high quality information for earthquakes and injection, because that is the two parameters that we will use for our causal analysis. We can use causal, we can create causal models, and we can verify those models by the observed data, this data-rich approach we described earlier. And of course, clarifying in any case if the causality of the seismicity, if it is either human or induced or natural seismicity. Next slide. Now, moving to the site selection considerations. Next slide, please. So for the site selection considerations, you have to remember all the time that most of the crust is in a frictional state of balance. Okay, the best oriented faults that follow the principal stress directions are close to failure. So if you change the stress or the pore pressure, any type of pore pressure next to them, that will create a slip, and they will create an earthquake. When in case the crust is in a stress equilibrium, there are no earthquakes, and there are anthropogenic activities coming up, like due to pressure changes, then the current stress is going to change, and then there will be a trigger of an earthquake cluster. Don't expect that when an earthquake is triggered, there will be no more earthquakes. That is a general rule. Usually seismicity doesn't start with a high magnitude earthquake, it starts with a smaller magnitude earthquake, and this will trigger an earthquake cluster that eventually might come up with a bigger magnitude earthquake. Next slide. Now, the pre-injection characterization is important. It's important to know if there is any existing seismic data, and when a site is close to an active zone, and thus can help us identify any stress information. When there is no previous seismic records, a local array is important in order to identify seismicity of less than magnitude 1. The earthquake monitoring, of course, must precede any activity or decision regarding the availability about the CO2 storage projects. So that's why we have to set up an array of seismic sensors to be able to monitor any type of seismicity in the area and identify background seismicity and any possible unknown active faults. Next slide. Now, in seismic array installations, one parameter which is important here, and I want to clarify first of all, is, and you have to keep it in mind in any type of earthquake monitoring project, is the magnitude of completeness. Magnitude of completeness is the lowest magnitude that an earthquake catalog is complete and includes all earthquakes that are from this magnitude and above for a specific area of interest and the time period. This is very important, and actually for any statistical analysis, one should use all the earthquakes that are down to magnitude of the completeness. If you use earthquakes that are lower than magnitude of completeness, you might get into misleading information. And if your magnitude of completeness is not good enough in order to understand the seismicity, the causal factors, mitigate the risk, then you have to improve your seismic network in that case. Now, things that are important for magnitude of completeness is the noise level. And that has been also, as we have seen in previous CCS monitoring projects, that because of the noise level, the magnitude of completeness has been very low, because the recordings on the ground motion systems have been so saturated by noise, so the small magnitude earthquakes couldn't be recorded or identified and detected. For the magnitude of completeness, people sometimes use simulations to identify them, but even if you do so, it is highly recommended to use observed data after you set up your array in order to verify your observed magnitude of completeness. Next slide, please. Now, there are three suggested arrays that we can use. One is the surface arrays, that we have instruments, seismic sensors deployed on the ground, on the surface. Those are low-cost systems. They are very low cost for deployment and maintenance among any type of arrays. You have to have a big number of stations to achieve a low magnitude of completeness. And for getting a good earthquake source information, especially the hypercentral depth, you have to have an accurate earthquake model in order to improve your accuracy. You have two main types of station geometry: concentral, secular, littoral, or stations along a 2 degrees that have a short station distance close to your area of interest. Next slide. Now, borehole arrays. Borehole arrays, they have the lowest detection threshold and magnitude completeness, of course, and highest accuracy in earthquake location. There are examples when you have 3 borehole arrays surrounding the area of interest, and then of course there are perforation shots to calibrate the array. The disadvantage of the borehole arrays is that they are very high cost, really very high cost. It's tenths or more than 20 times higher cost than the surface arrays in most cases. Sensors at geophone strings in that case extend to the depth of the investigation, and usually you need an accelerometer at least and a few seismometers on top of the array and the surface, just to make sure that in case of the high magnitude earthquake you can still have data that are not saturated. Next slide, please. Now, hybrid arrays is becoming more cost-efficient solution that people like. It is becoming more popular, and that is to minimize the cost. You can have a few boreholes around the area of interest, and then you have a small array also with sensors on top of the surface. On the borehole, you can use, in order to minimize the cost, you can use one of the boreholes used for site selections, so that you have to drill another two for the geoform strings. And of course, again, you need the perforation shots in order to calibrate your array. Next slide. Now, this is an example we have from IEAGHG geothermal field. They have 4 borehole arrays, 5 stations, and those through this array, they managed to have accurate spatial temporal clustering information, and also any type of geomechanical modeling they did for this area. It was possible to verify through the data they had from this array. Next slide, please. Now, moving to seismic event discrimination. There are usually what we do is we use statistical studies. That's pretty most common now. Seismicity in the seismicity world, it is the easiest thing you can do as soon as you have the seismic data. Of course, there are other approaches and we'll describe later on. But the good thing is that seismicity is coming up information are coming up very fast. Even the manual review data that you get in the next day or a few hours after the seismicity occurs, they are good enough to start some statistical models. Now, there is a case where we had a practical experience with public from certain events. That we had an Oversight example, where that was a small-scale project in 2003, where there were no small or microseismic earthquake during the project, and then has been a nearby felt earthquake of magnitude 6.6 in 2004, with no damage and no seismicity in the vicinity of injection reservoir. That was like unrelated events. It seems that the magnitude 6.6 earthquake has not been related to the human actions in the area. Next slide, please. Now, for the statistical, I'm keeping just one example here. That there is a few more in the report. Now, this is an example where what we try to do here for that is in West Texas. We try to identify the likelihood of seismicity related to unconventional fracking stimulation in hydraulic stimulation. Now, what we said here, because we know from the literature that seismicity, induced seismicity related to fracking is occurring during the time of the fracking and a few weeks after that. And also we know that it is very prompt. So it happened for a few days or weeks and then it stopped. So on the right-hand side, on the top right-hand side, you see the model we developed, where we say with the blue line, we say that the time dependence of the model. So we say that from the time that the fracking has started and one day after that, up to a few days, we have the highest likelihood that the seismicity that is in a close distance to the fracking well, it is related to the fracking process. Now, and then of course this likelihood drops with time. With the brown curve, we say that is the distance distribution, or we say if the distance to the lateral well is equal to 0, the likelihood is high, and that is up to a few kilometers away. Up to 4 kilometers is getting its highest value, and then it suddenly drops as we go further away. Now, we use this model. We actually run a lot of simulation models in order to identify, first of all, if those which are the best values for these parameters, the distance and time and the distance and space. And after we identify those values, we run the model again in order to identify where we see clustering of seismicity and the distance from lateral wells. And what you can see on the left-hand side of the map, you can see all the cases where we connect the hydraulic fracturing well, which is with the blue dot, with the earthquakes that are related with each well, which is with the green dots. And then on the lower part, on the right-hand side, you see an example when it is a cluster in the Jeff Davis Northeast County, where we provide with time the information on the fracking that started sometime in 2017, and we provide also the high volumes of fracking that they provide per day. And then before the end of the fracking, you can see with the red line, you can see the seismicity increasing, and it followed up for a few days, a few weeks after that. So that's a very nice example for fracking induced seismicity. Next slide, please. Now, what is important, it is to identify the hypocentral depth. And although any statistical models can be very helpful, it is important to understand also if the depth of seismicity is close to the area of the human activity. And that is becoming more and more important in cases where we have mixed cases, where we have fracking, we have saltwater disposal, in cases where we have a geothermal projects where they have also CO2 storage capacity. So all those things are coming up very rapidly, and it seems the hypocentral depth assessment is becoming very important. This is an example for the magnitude 4.9 earthquake of Menton that occurred back in 2020 here in West Texas. We used a local array on top and a local velocity model from this area, and we managed to have a high precision catalog. What you see here on this map, you see with the green green spheres, you see the relocated earthquakes. The blue square is the station on top that we had data from when the earthquake occurred, and the laterals you can see as well, the lateral wells. And there are two cross-sections, and yellow one that is along the strike, and the blue one that is perpendicular to the strike of the high precision seismicity distribution. Next slide, please. So here are the two cross-sections. You can see with blue the two different zones, the shallow and the deep ones, where we have the saltwater disposal. You see the lateral wells, the black lines, where you see the depth of the fracking, and you can see also the distribution of the relocated high precision earthquakes. And you can see that most of the seismicity is very close to the inside the deep injection zone, and actually it is related to the basement rooted faults that go from the basement to this deep injection zone. Next slide. Okay, now seismic hazard risk assessment and management. Now, there are four research areas for risk mitigation. Okay, now the first one is the spatiotemporal seismicity distribution. You have to have a monitoring system that can help you understand where the seismicity is migrating. It is pretty common when you have a triggering system that the seismicity will not stop only in one cluster. So the seismicity will most likely migrate to other areas. And that is something we see a lot in saltwater disposal injection induced seismicity, not so much, of course, in fracking induced seismicity. It is important also to understand the seismogenesis. And related to that, you have to use a mathematical approach, which is called template matching, in order to understand where you have the first small magnitude earthquake. So when the earthquake triggering occurred in this area. The third thing, which is important, is the high resolution earthquake location. That's coming out of event catalogs. As I described in my previous slides, it is important, especially not only for identifying the fault types and the fault strike and the subsurface rupture zone, but also identify the hypocentral depth. That is important. And then the last thing, in order to help you for hazard mitigation, is to identify and create your own statistical and semi-empirical models that can help you mitigate the risk. Next slide. Now, for risk of seismicity in the CCS projects now, we have seen there are three cases mostly. The first one is the public perception and concerns. Of course, even not doing anything and not starting a CCS project when someone is talking about it, there is a public perception and concerns about what will that entail, and if that will be has a high risk and relate to seismicity. Second thing is the damage to infrastructure at the injection site. For that, we don't expect actually with small magnitude earthquakes to have anything related to damage to this infrastructure. This infrastructure usually is available to manage high stress, so we don't expect anything like that. And of course, there is a damage to the subsurface in terms of CO2 containment, but this is something of concern. But lately, what we see is with a data-rich monitoring system, not only with seismicity but with other physical or chemical compounds, then it will not be necessary to have such concerns. Next slide, please. Now, the public perception, as I said, this is a frequent concern. Induced seismicity ranks in the top of 4 concerns when we reviewed the 135 studies, about equal to leakage risk and CCS effectiveness. There is a moratorium on injection. It's stop hydraulic stimulation derivative impact also on CCS. And the highest risk is to stop a project, lose the investment, and CO2 fail to be stored. That's mostly the case when we have concerns on the public perception side. Next slide. Now, the damage to infrastructure, as I said, the increased seismic hazard doesn't necessarily correspond to increased risk, okay? Because the main difference between the hazard and risk is the fragility of the infrastructure, okay? So the exposure, information that you have, and the fragility of the infrastructure itself. For that, the probabilistic seismic hazard assessment that's pretty common on any type of these projects can provide the likelihood area of study about the expected ground motion or the pre-ground acceleration, the pre-ground velocity, and then microseismic intensity and the exceeding value that someone might expect. But as I said earlier, we don't expect the infrastructure in CCS projects to be affected in any case, and the likelihood of damage is minimal in case of small to medium-sized ground motion. Next slide. Now, the proactive measures one can take is to, first of all, is the site characterization, okay? Select sites with minimal likelihood of induced seismicity, extensive monitoring at least for 6 months prior to the injection. In case you have induced seismicity, and in order to identify the low magnitude seismicity, you have to have an effective monitoring program. You have to make sure that you avoid any local noise that will affect your detectability. And of course, you have to have an adaptive seismicity assessment. That means that you have to even change your monitoring approach on depending on the seismicity, spatial temporal distribution, and any type of risk mitigation that it is of your interest. So you have to have a seismicity mitigation plan. Now, along with an adaptive risk mitigation plan, the idea should be to decrease the seismicity or avoid the migration of earthquakes close to the CO2 plume area that might affect protecting this area from any leakage. Next slide, please. Now, I added this slide just to clarify a few things. I think it's important to describe those important nodes. Now, small pore pressure change, that's what we see. These are from what we see here from in Texas and other areas in the United States, and a lot of publications follow those nodes. Small pore pressure changes can be the trigger mechanism of seismicity. Okay. Usually, what we see is that this is happening either when injection is close to the basement rooted faults, or that are very susceptible to provide a considerable magnitude seismicity, and also when the maximum stress direction is close to the strike of existing faults. In that case, the faults are susceptible to slip. Now, both processes, the effective pore pressure changes and related to seismicity, need to evolve to the first triggering event. For that, it is important to have a good monitoring system and also be aware and measure the bottom wall pressures and injection rates on a daily basis. Next slide, please. Now, the last part is the current state for induced seismicity modeling and forecasting. Now, current research is mainly in time-dependent earthquake hazard or earthquake hindcasting with its associated probabilities and errors. The earthquake hindcasting nowadays is coming out mostly from physics-based models, where we use the seismicity, the injected volumes, the pressure models, and this type of information in order to identify any changes in the expected seismicity. You should think of the seismicity is let's say the sensor, the phone, for underlying the physical process and providing the information and found the spatial and temporal nature of any physical process that is happening below, inside the Earth, subsurface. The model that characterize the feature of earthquake process mostly are probabilistic models, and they need to be calibrated based on data from earthquake catalogs. Next slide. Now, the United States Geological Survey provided in 2016 the first map of induced seismicity zones. As you can see on this map on the right-hand side, the wells associated with earthquakes are with blue. The green are the seismicity that is not associated with earthquakes. The oil and gas plays are with yellow, and the sedimentary bases are with brown color. And as you can see, at that time, already the area of Oklahoma has been very active and has been identifying a zone of induced seismicity. From the side in Texas, at that side, the South Texas, we have Fassing that has been in induced seismicity hydraulic simulation project, and the DFW area in Dallas-Fort Worth area, where we have soil water disposal being the causal factor of seismicity in activating faults that are close to the basement. And of course, the cocktail, which also described earlier by Sue, which is EOR. We had back in 2019, also we had 2 earthquakes of back 4 and above in this area. Next slide. So this is my last slide, actually, before moving back to Seyyed and Sue. I think I just wanted to let you know that there are usually 2 different approaches for seismic hazard. The one that is related to natural seismicity, and the one is related to induced seismicity. There are key parameters that are changing when you are doing that. They're calculating the seismic hazard for induced seismicity compared to the natural seismicity. Mostly it has to do with your catalog duration, your smoothing distance, and also the maximum magnitude that you expect. Those are the 3 parameters. I mean, the catalog duration, certainly you understand that is important, because it is important to have the most recent information about seismicity. Even in 1 year, sometimes it's not enough, especially if you want to use your hazard model for your daily operations. So you have to be more on that, on smaller catalog duration. Your smoothing distance for the approach that USGS used has been 10 kilometers, 20 kilometers. The approach we use currently here is 5 kilometers now. We think we can go to lower than that, especially depending on if we have a data-rich environment where we can use accurate earthquake location and rich injection information. And of course, the maximum magnitude is important here. USGS use magnitude 6. I would say that this is a good max maximum magnitude. I would say that for some cases, you should go to magnitude 5, especially when you are close to urban environments. Magnitude 5 earthquakes will certainly create some problems in areas that the distance between the urban environment and the seismicity is very small, like 10-20 kilometers. And of course, depends also on the type of buildings and if they have been built based on any seismic code. Now, the last thing is the ground motion model. That is a huge thing here. I mean, you have to use different ground motion models because the general and national hazard seismic models cannot apply very easily on that case. What I suggest for that is to use your own ground motion model based on your observed data. If you have observed earthquake data, use your own ground motion model based on that. So moving back to Seyyed and Sue now, thanks from my side.
All right. Thank you, Alexandros. Appreciate your talk. I have a few more slides, just quickly reviewing the regulatory oversight and then a couple of slides on outreach. I'll try to do it fast so we save some time to answer some of the questions I see in the chat. As far as the regulatory oversight goes, in the areas that there has been increased induced seismicity, there has been the regulatory authorities, they have defined rules and expectations for permitting. And what we have observed is there are two things that are common in most of these the regulations, which is one of them is looking at the past earthquake data, things like distance of seismicity from the injection wells and also the magnitude of the events. And also, like Alexandros mentioned, looking at doing a good job in characterization of the subsurface hazards prior to starting the project. In some cases, the operators has decided to follow the traffic light system. Basically what it is basically controls the actions and provides some guidance on risk mitigation based on the earthquake magnitude threshold. And in some cases, the operators has to provide some sort of a risk mitigation plan to the regulator to be followed if they are exceeding some sort of the magnitude that has been basically decided upon. In the report, we have studied quite a few number of states, countries, UK, Australia, Canada, Switzerland, but I'm giving just one example from Oklahoma, just give you a flavor of the things that you will see in the report and things that we have put together. Like in Oklahoma, they put together the traffic light system in 2013 when there was a concern over the increased amount of the induced seismicity due to the saltwater disposal mainly. And
Seyyed, we've lost sound.
Seyyed, we lost sound. Oops.
of an earthquake swarm or a magnitude 4 event, they were required to have a special permitting. And after having those events, they decided to also to increase the recording of the well pressure and volume, the injection volume from monthly to daily. And also another thing that they changed was that they were required to have mechanical integrity tests for injection wells that are injecting 20,000 barrels a day or more. It used to be every 5 years. Now they are requiring that to be done every year, or even more if it's being requested. And also they have a new definition for the area of interest, and based on that definition, there has to be a full review of the disposal wells coming with the permitting applications. Another thing that I wanted to mention is that it didn't only impacted the regulation, only didn't impact the actions that operators have to take. They also have to follow the new rules regarding the earthquake detection that is being in effect from December 2016. So some of those key changes which are now stricter compared to what it was before is that now operators are required to have access to a seismic array that would give them real-time information on earthquakes. And then mitigation actions must occur at the magnitude 2, which was previously at magnitude 2.5. And also some of the operators will need to pause operations for 6 hours when the magnitude of 2.5 is felt. This one used to be magnitude 3. So they are basically reducing those magnitudes and making the regulations to be a little bit stricter as far as induced seismicity goes. Just a quick couple of slides also on the outreach. We have reviewed a few outreach programs related to the induced seismicity. Attaining and maintaining social license to operate is widely recognized as a key element to site and operate these CCS projects. And it needs that information to be provided by trusted parties, and transparency in sharing the data remains important to have a positive project and a positive resolution of any conflict. The outreach activities are mainly to foster a positive engagement of the public and accurate reporting of the issues from the different sectorial activities, including CCS. And from what we saw in the reports, these strategies were mainly included use of digital and social media, public events and meetings, and education of the key audiences. Just a quick example of a successful outreach program. It's a Tomokomai CCS demonstration project in Japan. A few things that they did as part of their outreach program was they had panel exhibitions that they held in the city of Tomokomai and nearby cities. They had CCS forums for the citizens of the city of Tomokomai every year, starting of 2011. They had site tours. They had public events for people to go and see the observation wells. They had a very strong information disclosure system, so people can go to this website and access the injection volume, the pressure, temperature, and all that information related to the induced seismicity. They were running mini seminars for students at the universities, and also they had kids lab classes for primary and secondary schools to get them familiar with the global warming, CCS, and other elements of the CCS projects. And in 2018, in this site, they had a magnitude 7 or so earthquake, and it is reported that all the work that they did from 2011 was very helpful to deal with that magnitude 7 earthquake. That was a natural earthquake in the area, and basically making the people in the area to be feeling comfortable that that was a natural cause and it wasn't related to their operations. Our concluding remarks at the end of the presentation is that based on the available data from the CO2 storage projects, we see that there is a moderate coverage as far as the data goes, and it shows that the induced seismicity is similar to what we have seen or what we will be expecting to see in the saltwater disposal projects. We believe that there is a considerable learnings from saltwater disposal injection projects as far as the management goes, how the government is responding to these projects, and the numerous studies are really of high value for us to apply for CCS projects. A key element is that going forward, monitoring of induced seismicity should be like other parts of the monitoring of a storage project, and it has to be tied to the risk. Some sites may benefit from a strong investment in seismic monitoring, both to detect pressure changes and avoid risk. But at the same time, there could be projects that may have limited risk and limited value in the monitoring of induced seismicity maybe there. And our experience shows as well that project uncertainties can be reduced by available technologies during the characterization and permitting and operation. We are recommending that the investment in both historical data on seismicity, characterizing the faults, gathering false information and a state of stress is going to be very useful. And also during running a project, also collection of the data can further reduce the risk and basically avoid exceeding the limits that is being put by the government and regulatory agencies. And with that, that would be our end of our presentation, and we would be happy to take a few questions.
And thank you very much for that excellent coverage of the report of actually what is quite a complex area. We do have time just for one or two questions that have come in. let me just go to here. One of these refers to monitoring wells. Are monitoring wells of a permeable, producible horizon above the injection zone and to possible use for seepage recovery installation before CO2 injections commences?
I'll take
or
that one.
Are they not installed or present?
I'll take that one.
Okay.
One of the long known techniques for monitoring to ensure that fluids are retained in zone is to install a well in a shallower zone. We call this above zone monitoring. It's used widely for gas storage and hazardous wastes. It's not required as far as I know, but it can be part of a monitoring program. I don't think you would set it up for fluid recovery right off the bat. I think you you would be looking to get affirmation of the correctness of your model. Of course, and a monitoring well can be used for improving your seismic. But you can put geophones in one. But if you did, you probably wouldn't use it for recovery. You'd probably cement them in.
Okay, thanks, Sue. Another one here, background seismicity level. Does it assume that all variations from background are abnormal, or is it evaluated based on regional larger background levels as well? Who'd like to take that one?
I'll take that one. So,
okay.
Background seismicity, it assumes all variation from background should be are considered normal, not abnormal. So you have to be aware of the background seismicity, and in that case, any changes from that background will be considered abnormal, but it will be in this specific area of interest. So you should not. It depends on the size of your area. Usually, background seismicity is measured in larger scale, but we have the specific area of interest now, so we have to consider only for that area background level seismicity and abnormal assessment for anything that we see in this area.
Okay, thank you. And what duration of pre-injection seismic monitoring is recommended, optimally and minimally?
Minimally 6 months prior to any type of injection, in order to get the local background seismicity.
Okay.
That is the minimally. The optimally, it can be more than that, like a year. But I suppose that I assume that it would be nice to have a background seismicity on the site characterization process as well.
Okay. And there are some other questions, but we're really more or less out of time, and I'll forward these on and address them. But there is one final question, and that is, there have been instances, I must stress, not related to CO2 storage, but definitely associated with induced seismicity. And that is quite large events, sort of magnitude 5, 6, which are known to have been propagated from faults in deep crystalline basement. And what's your view on how or if these can be detected, and if so, how can you determine the stress regime acting on them, and whether they are vulnerable to being triggered by, say, fluid injection?
I can start, and then Sue and Seyyed can mention something. So certainly, we consider the crystalline basement faults of the highest seismic hazard. Okay, because most of those faults, they are brittle material. They have they cover a higher subsurface rupture zone, so they are related to higher magnitude earthquakes, expected higher magnitude earthquakes. In order to avoid triggering those faults, you have to make sure that any type of your human activity is far away from that. so that any stress accumulation from that's coming out from your human activities doesn't go down there. That it diffuses going down to these basement rooted faults. So you don't trigger any seismicity in this related to those faults.
Okay. So, have you a view on this?
Yeah, that's what they did at the Decatur project when they drilled a second well intending to go to larger volumes. To avoid energizing the basement, they just moved up so that they had an effective geologic cushion to buffer zone to attenuate any fluid intrusion into the basement to de-risk that situation.
And of course, the pressure regime is carefully monitored in the injection zone.
Well, you have the problem is that the state of stress varies. It's not homogeneous to the system. So the state of stress in the brittle crust can be quite a lot higher than is in the injection zone, and surprise you, which has been the situation in some places in the mid-continent. So monitoring the injection zone is required, but also understanding the distribution of data stress so that you've got the right assumptions.
Okay, thank you. Well, that brings us to the conclusion of this webinar. I'd like to thank Sue, Seyyed and Alexandros for giving us a very thorough summary of the work that they've done. And as I say, that this report will be published in about the next 3 or 4 months. By published, I mean available, downloadable from our website. So thank you again, and I'd like to thank all the people that have participated and tuned in. Please look out for further webinars. We are planning to produce a webinar on most of the work that we produce. And with that, I will draw this webinar to a close. Thank you very much.
Thank you.
Thank you.
Thank you.